And first, thank you very much for having me in your seminar. And what I want to talk about today is causal structures and causal borders, and why they matter for agency, autonomy, and consciousness. I will, however, start with a more or less brief introduction of integrated information theory, because A, that's what people usually want to hear, and B, it does provide the motivation and also the foundation of the measures that I'm using for the work on agency and autonomy. So IIT, you probably have heard of it if you haven't read one of the papers even, has been conceived by Giulio Tononi, and this is now 20 years ago that I think the first paper came out with the integrated information or information integration in the title as a theory of consciousness. And since then, there's been a lot of work that tried to improve on and make the mathematical framework and conceptual framework too behind IIT more coherent, mostly. So in line with the underlying notions about what consciousness is and how we can identify it in the physical world. And so in 2014, we published what is called the Integrated Information 3.0. That's when we started to label the versions. And so that's the first one that I was majorly involved in. And now just last year, we published 4.0, which at least Giulio views as the first sort of complete version where he actually tried to address like all aspects of the theory that he knew need to be addressed at some point, right? And so consciousness, even in the neuroscience of consciousness field, not everybody agrees about what it means to be conscious. And so I always start with this disclaimer that when I talk about consciousness, I really mean what it is like to be a thing, so that there's some feeling associated to just be, right? You exist in the world and it feels like something to exist and to have these experiences. So this means that in my definition, consciousness is not just a reflection of one's experience. It's not just about the environment or the contents of the experiences. In this sense of consciousness, someone who is dreaming is clearly conscious. So they are having experiences and they are conscious even though they are asleep. And consequently, it also means that consciousness is not just about responsiveness. So it's not about whether one can react to a stimulus or not, in however complicated manner. So any theory of consciousness that wants to address this problem should be trying to account for the experience itself, what it is, why it feels the way it does, and why it has to do with some parts of the brain rather than others. There is a neuroscience of consciousness, and over the last maybe 30 years, what it mainly was trying to address was yes or no questions about consciousness. So we have some stimuli that get that set the brain in, and then we're trying to find neural correlates of the experiences, and the questions that are asked are usually, is this person conscious or unconscious, or is this person conscious of a particular stimulus that might be almost subliminal, like hard to see. And then those yes or no states can be contrasted to measure correlates of consciousness. However, and this has been kind of pushed by the whole group working on IIT, is that there can be a science beyond just these yes or no questions. And the two obvious ways to tackle this problem at least if you come from IIT, are to describe the structure of the experience. So how the different aspects, and we sometimes call them quale, or within the IIT language, the distinctions within your current experience here and now relate to each other. So there's something on the left, something on the right, there's a book that is blue, your orange sweater, and so on. And also how the structure of the experiences differ with respect to each other. They can also teach us something and can be experimentally evaluated. And the other way to go beyond just yes or no questions is to ask about the extent of the substrate of the experience. So this is about where in the brain and also at which level of description is the true substrate of consciousness. So we already know that there are many neurons in the brain that are not involved in creating your conscious experience. For example, there's the cerebellum, which has even more neurons than the entire cortex, and yet it doesn't seem like it's contributing at least to our experience, the one we have on a day-to-day level. And the same is true for the spinal cord, which is also directly connected to the brainstem and the brain. So given that all these are interacting components, how do we decide that some part directly contributes to the experience and some part doesn't? And in a similar way, there's a why question on why do neurons seem to matter in the first place? Why don't we have to describe the brain at the level of atoms or molecules to capture aspects of our experience, right? And all these why questions should ideally have some answers that are directly motivated by the proposed theory of consciousness. And something that is relevant to the later part of the talk on agency and so on is that these two ways to go beyond yes or no questions in consciousness science also show that it's not just what a system does that matters for consciousness and agency and so structures and borders, but it really matters how the system does what it does and the specific implementation of its functions. And this is just my provocative statement that I think functionalism, pure functionalism at least, cannot be correct because of these two problems. So what is IIT trying to do? The methodology of IIT is something that is really that separates it, that highlights how it's a new way of tackling this problem. And the way that IIT starts is by really just asking what to characterize the phenomenal experience, so your experiences itself. So first you try to identify all the characteristics of what you want to explain in the first place, right? You want to really know what are the features of your explanandum. And so to do that, IIT identifies the essential properties of every experience. So properties that every experience has and that therefore are necessary to count as a conscious experience. And then we ask how these essential properties could be translated to characteristics of the physical substrate. So if there are essential properties of consciousness, how could a physical system be structured so that it can capture or underlie these essential features? And there is an important notion in here that is not about consciousness, but about how we view the physical world. And basically, we view the physical as whatever you can manipulate and observe, which ultimately means that the physical is about causes and effects. So a physical unit is something that can be manipulated and can be observed by other physical units. And therefore, the whole formalism of IIT in the end is formalized in terms of relational properties, in terms of cause-effect power. Okay, so and how these causes and effects are structured can then be translated in what is illustrated here by this fancy structure. And that fancy structure should then correspond to the experience that the system, the substrate, has in its current state right here, right now. And so there can be a backward force where we go around and try to establish that with the postulates we require of the physical substrate, we actually capture what we wanted to capture in the experience that we're sort of introspecting and characterizing. And this can go on for quite a while. And again, so there's this distinction between the essential properties, the properties that every experience has to have to even count as a conscious experience. And then there are accidental properties that are properties of your current experience right here, right now, and that could be different in another experience. So for example, part of most experiences, but not necessarily all, is some feeling of extendedness, that that there is some space, for example, a visual space, that a lot of the objects and parts of your experience are located. And there can also be sound experiences of temporal flow. For example, if we hear some melody, or just what are objects in the first place, right? So all these are accidental properties that in the end, if we have the unfolded causal structure of the underlying substrate, we should be able to account for every accidental property, just starting from requiring the essential properties and then building up from there. Okay, so this is the theory building part. And then, of course, there's also a validation part. And that means that we can take the theory and then apply it to healthy human subjects, where we can trust their report on whether they are consciously experience something or not, or in which way, how their experience feels right now. And we can see if the predictions of the theory onto about what the substrate is supposed to experience, how what the substrate is in the first place in that experiment, how that matches with the experimental results. And then finally, when we're reasonably sure that we're on the right track with our predictions, then we can apply the theory to subjects and objects that are very different from just healthy adult human subjects, and use it to extrapolate to gain knowledge about the conscious experiences or the absence of consciousness in these systems, right? And I think an important point to make here is that this is not a test of the theory, right? The extrapolation, subjects that are very different from human subjects, there's no test to be made here, because there really is no theory independent way to tell whether a system that is very different from yourself as a conscious being is also conscious, right? So these are not predictions, that there are extrapolations. The predictions are the ones that you can validate or falsify. And those predictions are always tested in healthy human subjects or very closely related physical substrates. Okay, so what are the essential properties of every experience? So the first one, which might seem trivial but is still contested, is that we start with the fact that consciousness exists, phenomenality exists. This means that it must have as its substrate something that also physically exists. And so just this starting point, which we call like the zeroth axiom and postulate, shows the difference between the axioms and postulates. The axioms are taken from the intrinsic perspective, so it's the experience of the subject that has the experience, right? And then we want to translate this into a third-person account of an experimenter who's trying to see, identify whether, you know, the subject, the experimental subject, is conscious in that case. And so we start with a substrate that is characterized by interacting units. So as I said, a physical unit is something that has to be able to be manipulated and observed by other physical units. And what this means is that ultimately the physical universe, according to IIT, is nothing but relational properties between physical units. So this is very provocative. It's also not clear that it's 100% true, right? It's basically an assumption that falls out of IIT. But if you think, for example, about a quantum mechanical description of the universe, it pretty much looks like this, right? So what is an electron? An electron really is just a description of what it means for this unit to interact in a certain way with other units, right? So there's nothing else intrinsic about an electron. And in the same way, there are just no intrinsic properties to physical systems in IIT, physical units. So everything is based on what happens when I wiggle one unit, what effect does that have on the other units? And this can be described in what is called the transition probability matrix, at least if we're talking about discrete units, which of course is a simplification, but that's where we start for the moment. Okay, so finally, the essential properties. The essential properties that IIT identified about the experiences are that every experience is intrinsic. It exists for itself, not for someone else. It is informative, it is specific, it's the way it is. So this is a bit of a tautology, but what it means is that there is something about it right here and right now that determines its character. And that also makes it different from all sorts of other experiences that we can have. Every experience is unitary, it is integrated. It wouldn't make any sense to assume that it can, it's not one, because once you are able to sort of experience the two halves of your experiences separately, you don't have one experience anymore, you have two. So this, I think, integration best makes the point that these essential properties are really, really, really basic properties. So we're not making any grandiose psychophysical claims here. It's really the most basic requirements for what it means almost to be just something, to exist as something for itself, right? And the for itself is really what makes the difference between just existing as a thing, you know, like my cup of coffee here, versus existing for itself, which then means there's some feeling of what it is like to be, right? Because you're existing for yourself. And everything, so the exclusion cost, sorry, axiom means that there is some boundary. So again, there's a boundary to the something. There's things that are within my, or there's distinctions, aspects of the experience that are inside my experience. And then there are other things that do not make it into my experience, right? There's also definitely a border between my experience and your experience. I'm not experiencing what you're experiencing. You're in a different spot of the world, right? So if we describe the universe as interacting components, that universe will have to parcellate into separate, discrete conscious experiences. So we have to be able to delineate what's in the experience and what's outside of the experience. And then finally, there's the axiom of composition, that every experience is structured in some way or another. And so I've already taken some of this up front, but we're applying the same reasoning to physical substrates now. So the physical substrate is supposed to exist for itself in terms of cause-effect power. So something exists for other things if it can take a difference and make a difference to something else. It exists for itself if it can take a difference and make a difference to itself. And so what we're looking at are the cause-effect relations within our candidate substrate, and not the behavior of the substrate with respect to other outside entities or units. We're looking at whether this set of units is informative, and here we evaluate is whether it has information about its causes and possible causes, and information about its possible effects. Whether it is integrated, whether I can partition the causes and effects that happen within the system into separate entities. Of course, you know, if you have two systems that never ever interact with each other, it would be very counterintuitive to assume that they could give rise to a unified experience, right? So we require the substrate to be integrated, and we require the substrate to have self-defined borders. And this is the only part that is a bit, there are several steps to understanding what that means. So if we take a system, for example, your brain, right, and we measure its integrated information value, we'll most likely find a positive quantity because everything is at least indirectly connected to everything here, right? And information is obviously getting passed around. Now, if I take your substrate of consciousness within your brain plus 10 neurons or minus 10 neurons, it will still have a very high value of integrated information. So it's not like only conscious systems have integrated information. And this isn't just true for integrated information, it's true for almost every computational property you could define over a neural network, right? So there's no sharp boundaries of yes, no, this is my system. So how would we find borders in an object, in an objective manner? And the solution that is proposed by IT is that we find the system that is a maximum of integrated information. And the reasoning here is that so we have to find an explanation for why it is this set of neurons and not 10 neurons more or less. And the justification would be, well, it's the one that maximizes it, which we often sort of loosely refer to, for example, the principle of least action in physics. So we find the substrate that is maximal And maybe another comment here is that this is complicated from the perspective of the scientist who wants to identify the substrate, but it's not complicated from the being that is the physical substrate, right? So nature just has that fact as a fact, and therefore the substrate is what it is. It's just that for us, it's complicated to identify the substrate. Final part is about unfolding all the cause-effect relations of the units to get what we call the causal structure of the system. And I will talk about this a little bit later. Here, I just want to make the additional point that all this math is computed from this transition probability matrix of, in principle, the universe, but in practice, the substrate plus some known inputs and outputs to the substrate. Okay, and again, so what IIT then claims is that there is an identity between the experience of the subject right here and right now with the unfolded cause-effect structure of the substrate in its current state right here and right now. And there are some quantities that we can compute. One is so the integrated information of the substrate that allows us to identify the substrate. And then the unfolded structure has a quantity which in IIT 4.0 is the big phi quantity, which is just the sum over all the distinctions and the relations in that structure. And that determines sort of the quantity of consciousness, which here could be just interpreted as the richness of the experience. So how many distinctions are there and how related are those with each other? So to get the connection to the second half of the talk, I want to talk a bit more about the measure, the integrated information measure that we call system integrated information that we use to identify the substrate of the experience. And so in principle, a very simple test for any theory of consciousness is to put a certain number of people in a room, apply the theory to the physical system that describes the room with the people, and ask how many consciousnesses are in that room. And the answer should be at least 3. And yet, basically, no, at least neuroscientific theory of consciousness is able to do that, or is even designed to be able to do that, because usually we start with the background knowledge that we assume that the brain is the seat of consciousness, right? But I do think it's very important to take a step back and ask about not just the neuroscience questions, but also to view consciousness as a physical property in our universe. And then this becomes a very important question of how do we identify the subjects within a physical system. And there are no real good ways to do that provided by physics at the moment. So what we want is an observer-independent way of identifying the borders of a system. So of course, I could say, oh, I can find mass densities, that would probably find me the people and objects in a room, but not in a discrete way, not in an absolute way. And, it also doesn't identify the essential characteristics here, right? Like a block of iron would have a higher mass density than my brain, of course, right? So we're really trying to find ways that identify the sources of interaction in an absolute way, so that we can draw our borders around, really distinguish what is a subject, what is an agent, what is a conscious being, and what is the environment that it is interacting with. And so the proposal by IIT is to start with the first four postulates, that what is required is the intrinsicality, information, integration, and exclusion. And if I have a maximum of cause-effect power, evaluated by the system integrated information, that is a substrate consciousness. Now, basically the same formalism with slightly weakened exclusion postulate can give me borders around systems that are hanging together very well in an informational sense, right? So, for example, I expect the substrate of consciousness in my brain to have the highest value of integrated information, but maybe, you know, my brain as a whole will also have a local maximum of integrated information, and my body might have a local maximum of integrated information within the greater environment of this room, you know, and so I can use a weakened version of the exclusion postulate together with the system integrated information to identify subjects and objects within a larger environment. And so I've done some work trying to apply these measures to answer this question. So how do we distinguish an agent from its environment? And here to pose the problem again is we have some agent with sensors and motors, and it's clearly interacting with some environment, right? But if we know that, and let's say we know exactly how the dynamics work of this larger environment that includes the agent, how can I identify a partition between the agent and the environment? And here, how do I do so in an intrinsic observer independent way? Because, you know, what says that the agent is here? Why not a bit larger, a bit smaller? Okay, so so the one aspect is, of course, that an agent or anything that stands separate from a background of external influences should be integrated in its internal influences. So there should be something that exists as a whole above all the background of the external influences. And so a first requirement that comes from IIT is that any agent is a recurrent system or requires recurrent connection. So that means, and the reasoning here is that if I have such a feed-forward system, right, there just is no way to draw borders around a subset of these systems because who says, you know, that these are inputs, these are outputs, and what is inside is intrinsic to the agent, right? Why I could just as well call these outputs or these inputs and these inputs. So that's the reasoning why we want to have integrated agents. And so we applied some of these to actual simulations of these, I like to call them animates, with their sensors and motors and hidden neurons, which are just binary nodes that can interact in this case, deterministic way, following generalized logic rules. So basically, a transition probability matrix lookup table of given their the state of their sensors and the state of their hidden units, we can update the next state of the hidden units and the state of their motors. And these connections are evolved using a artificial simulation algorithm so that they get better and better at performing a certain task. And the task in our more recent studies is that they have to traverse a maze, and they get shown symbols for left and right, but there are two conditions. One is the easy condition where the symbols are fixed. And then the more difficult task is that they're the symbols are randomly chosen at the beginning of each trial. So the agent first has to identify which symbol is associated with left and right. And perfect agents can do that by making maximally one mistake in the beginning, and then they sort of have the memory of what the left and right symbol correspond to. So these agents evolve to have pretty high fitness. Of course, the association conditions are more difficult than the non-association conditions, but we focus on the perfect agents so that we can actually know that these agents implement a solution to the problem of the environment. And so when we compare the possible solutions that evolved, so these are two agents, two example agents that both perfectly solve the association task, right? So behaviorally, these agents are identical. And now we can compare, and we find that there are agents that do so using a feed-forward structure. So there's still self-loops on those nodes, right? But all the information flow is in one direction. There's no information that gets fed back into the system. And then we have an agent with a massively recurrent structure who also performs the same task. And so the judgment call here based on IIT is that even though these two agents are doing the same thing, right? This could be, or this fulfills, I would say, the minimal required characteristics of being an autonomous agent, whereas this one does not, right? So this to say that the implication that follows from the logic about what makes, you know, a thing that stands out above the influences of the environment, we can have two systems that from the outside look identical, but if we look under the hood of what happens, here we have no autonomous agent, whereas here we could have them. And as an interesting side, we found in an earlier study that the more sensors we give to the agent, the less internal complexity there is. So if we, for example, take away one sensor, then the agents that are still able to reach high fitness in the task, which is the dark orange line here, they will evolve higher integrated information than the baseline agents that have two sensors. And I think that makes a lot of sense because basically they have to perform the computations internally to understand where they have to go. Whereas with more sensors, you can compute things in a much more parallelized and less integrated way. So an example to show that is that if you take your digital camera, which is now also obsolete, you take your iPhone, right? And you take a picture, the pixels, you know, the set of pixels on the chip can just display any complex picture they want, but they do so in a completely non-integrated manner, right? And that means that the behavior is entirely driven by the environment. Whereas if you have to have internal complex computations, the likelihood that there will be an integrated system inside becomes much higher, at least in the context of these agents. So to summarize, simple tasks at least can be solved both in a modular and an integrated manner. And the same holds true also for complex behavior, as we know now, given our advances in IIT. And so our advances in IIT, yes, but in AI, actually. So if you have something like ChatGPT, which is not technically a neural network, but it does work in an entirely feed-forward manner, even if it mimics our behavior very well, you know, the analysis would be that it could not count as an autonomous or a conscious agent because it lacks the recurrent flow of information that is required to give it an existence as something above the background of the environmental forces. Okay, so implementation matters for agency and autonomy is the take-home message. And here's another example that I hope will drive that point home. So as I said, if a system is described just by these transition probabilities of its interacting units, have a certain TPM that describes the global dynamics of the system embedded in the wider universe environment of that system. Now I could have, for example, this little 3-node system. What it does is it just cycles through its binary states, right? So we have 0, 0, 1 turns into 1, 0, 0, and there are these 8 states that the system will cycle through, and I can call those 8 states just 0, 1, 2, 3, 4, 5, 6, 7. This system has an integrated information value of 2 bits, or I bits as we call them. Now I can just scramble up the labels here, and the system will still be performing the exact same global function, right? So it still cycles through its states, 0, 1, 2, 3, 4, 5. But now what those states mean with respect to the elements has changed. And so this global remapping leads to a different underlying network structure, a different causal network. And it can happen, as in this case, that this other structure has an integrated information value of 0 because there's feed-forward aspects to it in this case. And so there was a paper written that basically criticized IIT on this basis because the premise was that, well, they are doing the same thing. Their global function is identical. Shouldn't they be equally conscious? And so I wrote a reply that was it's not really a reply. I wrote the paper that was motivated, however, by this statement to show that it's not just for consciousness that we're saying, no, the implementation matters, but also just the distinction between an agent and its environment depends on the substructure. So we cannot just assume, for example, that if the global function of a system and the environment is maintained, that we find the same number of agents or things within that system, right? So here, I know this is a bit of a complicated diagram illustration, but the essence is there was also, again, this system plus environment is cycling through its possible dynamical states. Also, the subsystem is cycling through its states. When I do the global remapping, I maintain the global dynamics of the system, but of course I destroy the dynamics of the subsystems. So global remappings are not innocent with respect to the subsystems and their existence within that larger system. So this to say that even if you don't think this has anything to do with consciousness, global remappings that maintain the function of a system are not innocent when it comes to agents, environment partitions, and questions of autonomy, and then also by extrapolation, questions about consciousness. Okay, and then I want to take maybe a few more minutes to talk about causal structures now that we've talked about causal borders. So this is the last part. This is the composition that once we have identified the substrate of consciousness, we can unfold all the different ways in which the units within that system, but also combination of units within that system, constrain the rest of the system. So for every for every what we call mechanism, but it's actually every subset within the substrate here, we can ask what does this subset, for example, what does unit A say was its cause within the system and is going to be its effect within the system. And we can ask that in a structured way, right, in a hierarchical way, for all the substrates up to the for all the subsets up to the full system. So what is the prediction and retrodiction about the cause and the effect of that substrate? And so, for example, element C here, if it is off, it will say that element A was off, and it will say that element D within the system will be off, right? And so I have these specifications for every subset, and I call those distinctions, and then what they say can also be related. So for example, the mechanism CD, the combination of units C and D, might say that element A must have been off, given that they are in the state they are in. And the combined mechanism BCD might say that A and C must have been off. And so there's a relation between the potential causes they specify and the potential effects they specify here. So with another unit. So the structure, the causal structure, is composed of these distinctions and then connected by the relations between the distinctions. So this gives me a particular cause-effect structure based on the transition probability matrix of the system. And we use this structure to explain the content of certain experiences. And so this is a research project that's ongoing. And for example, one paper that is already out is the Hahn and Tononi paper 2019, where they used assumed substrate for topographic visual cortex, let's say, and unfolded its causal structure to show that the way that the relations and distinctions of that substrate work, yeah, I should show it. So there's a topological substrate. We unfolded it to look at the distinctions and the relational properties of that structure, and found that the relational properties of the structure match the relational properties that are required of a spatially extended experience, right? And I did not say enough to make this understandable, but please look at the paper if you're interested. And so the paper that tries to do the same mapping between the unfolded structure of a substrate and specific parts of an experience is now almost submitted for an experience of the flow of time. And there's also already work about what it means to be an object, an invariant within the experience. So the hope is to be able to do this for more and more parts of experiences, to then make predictions about which substrates have to be involved in certain experiences, and that can be then verified using neuroscientific measures. All right. However, so this causal structure is, again, not just relevant for explaining consciousness and experiences. It is, in fact, also relevant for explaining behaviors. And this is what we tried to show in this paper, the Causal Reductionism and Causal Structures paper. And there we also started again with like little creatures that we called frogs that behave in an environment where there are left and right bugs that look this way in black and white, and then there are super bugs that have to be avoided. And so the basic kind of frogs has 3 internal units, 3 neurons, and 3 sensors for detecting what's in front of it. And then 2 motors, which can either make it jump left, jump right, or jump forward if they're both activated. So if that frog sees a superbug, right, it will have this sensory input, black, white, black, which then activates the center neuron, which activates both of the sensors. And so we can ask what caused what. So this is the description of what happens inside the frog, right? And now we make things more complicated by saying that there are 3 types of frogs. These 2, so there's the second type that works the same way, but instead of having 3 internal units, it has just 2 over which all the possible behaviors are encoded, but it basically works the same way as this F3 frogs which has a specific unit to trigger the jumping behavior. And then we have these F1 frogs, which are weird little half frogs that act like a full frog when they are found next to each other and confronted by a superbug. So if you have 2 of those together and they are confronted by a superbug, they again will just jump over it and then maybe go their separate ways. But the point is that their behavior, even though there are 2 individuals, right, looks very much like the behavior of these regular frogs. Now, using our causal structure analysis based on the principles of IIT, we can ask what caused the jumping behavior in each of these cases. And we find that, as you would expect, the cause of the jump in the 3-neuron frog is the middle neuron. The cause in the 2-mechanism frog, the 2-neuron frog, is the joint higher order mechanism of the 2 internal units combined. And in the 2 half frogs, though, there is no integrated mechanism that explains their behavior. Instead, their behavior can be reduced on the individual behavior of the one frog using its left neuron and the other frog using its internal neuron. So all this long story, what do I want with that? In all of these cases, we can easily predict the behavior from the individual neurons. But causation is not prediction. And so the point here is that if we ask, does each of these frogs have a mechanism to avoid superbugs, then yes, that is true for this frog and this frog, but I hope intuitively you'll see it cannot be true for the half frogs that are 2 separate individuals. They don't have a mechanism to avoid superbugs. It just happens that their behavior is similar to the other 2 frogs when they find each other next to each other. And then are there irreducible mechanisms according to causal reductionists? So a causal reductionist, I didn't explain, would be someone who only ascribes causal power to the physical units themselves. So every neuron does something. Groups of neurons can be reduced to the behavior of the individual neurons, and then that typically leads down the road to a reductionist explanation of consciousness, a la Francis Crick, who says, you and all your hopes and dreams and whatnot are just this bag of neurons that makes up your brain, right? So here we have 3 mechanisms, here we have 2 mechanisms, and here we also have 2 mechanisms according to this definition. Now, all 3 of these systems, we can perfectly predict the behavior, right? But the problem is that the causal reductionist conflates the ability to predict with the causal explanation. And so if we actually try to provide a causal explanation for the mechanisms, the causal reductionist cannot, because the mechanisms are the same here and here in a reductionist sense. And yet there has to be an explanation given for this F2 frog with the distributed computation, but not for the other two frogs. So there is an inherent inconsistency in trying to describe the behavior of these three frogs in a reductionist manner. And that's what we wanted to highlight here. And that's where the importance of causal structures, just for describing the behaviors of agents and entities, comes in. And that's it. I talked the whole